on the class of soil and rock mechanics. So I hope you all are safe and doing well. So in the previous discussion we have seen, I have discussed two chapters, that is first one is lateral earth pressure theory and the second one is stability of slope. So today I am going to discuss another very important chapter, that is shear strength of soil, and in shear strength of soil we will see how to compute the shear strength of soil like Mohr-Coulomb theory and modified Mohr-Coulomb theory I will discuss. And before that I will discuss what is the normal stress and shear stress acting on the soil, and after that I will discuss various laboratory tests like direct shear test, triaxial test, unconfined compressive strength test, vane shear test, and after that I will discuss some field tests, that is vane shear test, standard penetration test and cone penetration test. Let us discuss about shear strength of soil. So before that I will tell you that what is shear strength. So shear strength of soil is the resistance offered by the soil grains against shear deformation. If soil has not sufficient shear strength, then it may be fail as a shear failure, and shear failure can be fail in the form of failure of infinite slope, failure of finite slope, failure of soil below a building foundation. So let us discuss what is shear strength. So shear strength of a soil is the resistance offered by the soil grains against shear deformation. Example of shear failure. Example of shear failure. The first example is failure of infinite slope. What is infinite slope? We have already discussed in the previous discussion. Failure of finite slope. The failure of soil below a building foundation, and failure of soil below a building foundation in the form of general shear failure, local shear failure, and punching shear failure. So what is general shear failure, local shear failure, and punching shear failure? This thing I will discuss in the coming subject, that is foundation engineering. I will discuss in detail what is general shear failure, local shear failure, and punching shear failure. So shear strength of soil I have defined. It is the resistance offered by the soil grains against shear deformation. And if the soil has not sufficient amount of shear strength, then it will fail as a shear failure, and shear failure can be fail in the form of failure of infinite slope, failure of finite slope, and failure of soil below a building foundation. So let us take 2D analysis. So if this is the block, this is the major principal stress and this is the minor principal stress, and consider a plane AA at an angle theta with the major principal plane theta. So let us assume failure will occur along this plane. So this plane, two stress, that is one is normal stress and the second one is shear stress, and a resultant stress acting at an angle of beta with the normal stress, where beta is the angle of obliquity and theta is the failure plane angle. So what is the expression? So we have already discussed in the solid mechanics the expression of normal stress and shear stress. So just I am writing for the brush up. Consider a plane AA at angle theta with major principal plane. The normal stress can be computed sigma 1 plus sigma 3 by 2 plus sigma 1 minus sigma 3 by 2 into cos 2 theta. In the solid mechanics, I have written sigma n is equal to sigma 1 cos square theta plus sigma 3 sin square theta plus 2 tau xy sin theta cos theta. Similarly, tangential stress is equal to sigma 1 minus sigma 3 by 2 sin 2 theta. So these are the expression of normal stress and shear stress. So we know that resultant stress is equal to sigma n square plus tau square plus 2 into sigma n into tau into cos theta, and normal stress and shear stress is at an angle of 90 degrees, so this component will vanishes. So resultant stress will be the square of normal stress plus shear stress. Similarly, angle of obliquity can be computed. So tan beta is equal to ratio of shear stress, tangential shear stress by normal stress, where beta is the angle of obliquity. The shear failure will occur on that plane in which resultant stress is most inclined with the normal of that plane, and such plane is called failure plane or critical plane If failure plane AA becomes critical plane, then angle theta is called critical angle theta c. So this theta c can be computed. I will show you the value of theta c with major principal stress and minor principal stress. So if I draw Mohr circle, so Mohr circle I have already discussed in the solid mechanics. Mohr circle for sand. So if I draw Mohr circle for sand, so we know for sand the value of cohesion is equal to 0, but angle of internal friction will exist. So Mohr circle is the graphical representation of shear stress and normal stress on the x-axis and shear stress on the y-axis. So let us assume this is the major principal stress and this is the minor principal stress. So if I draw Mohr circle, so this is the Mohr circle, this value is sigma 1 and this value is sigma 3, and if I draw a failure envelope, and this is the center, let us assume this is the 2 theta c, this value is angle of internal friction, and this is Mohr failure envelope. I will discuss in the subsequent class what is Mohr failure envelope. So this value in triangle OBC, if this is 2 theta c, then this value is 180 minus 2 theta c, So in triangle OBC, phi plus 90 degree, this angle is 90, plus 180 minus 2 theta c is equal to 180. So theta c is equal to 45 plus phi by 2. So critical angle is 45 plus phi by 2. So dear student, till now we have discussed what is shear strength and what is the different shear failure if the soil does not have sufficient quantity of shear strength. And after that I have written the expression of normal stress and tangential shear stress and defined what is angle of obliquity. And after that I have drawn a Mohr circle for a sand, and we have seen the critical angle is 45 plus phi by 2 with the horizontal or with the measured principal stress. Similarly, if I am interested to know the critical angle with the minor principal axis or with the vertical axis, then it will be 45 minus phi by 2. So after that I am going to discuss, I will show you that Mohr circle for the clay and Mohr circle for the silt, and there is a relation between major principal stress, minor principal stress, cohesion and angle of internal friction that will be derived. And after that I will discuss what is Mohr failure envelope, Mohr-Coulomb, what is Mohr-Coulomb criteria. So after that I am going to draw the Mohr circle for clay. So we know Mohr circle for clay. So for clay, cohesion is equal to, cohesion will exist but angle of internal friction will be 0. So Mohr circle is the graphical representation of shear stress to the normal stress. This is the Mohr circle for the clay. Major principal stress, minor principal stress. This is the center of the Mohr circle, and this is the cohesion, and angle of internal friction is equal to 0. Similarly, if I draw Mohr circle for silt, Mohr circle for silt. So in this condition, both cohesion and angle of internal friction will exist. So this is more practical case. This is shear strength. So if I draw a Mohr circle, this is the major principal stress, this is the minor principal stress, and if I draw a Mohr-Coulomb envelope, so this is the Mohr-Coulomb envelope, and it will make an angle of phi with the horizontal O dash. This is the origin O, and this is the center of the Mohr circle. So this angle is 2 theta. ABO. So we know this value is sigma 1, major principal stress, and this value is sigma 3. So what is the diameter of the Mohr circle? Sigma 1 minus sigma 3. So what is the radius of the Mohr circle? Sigma 1 minus sigma 3 by 2. So this length is sigma 3 plus sigma 1 minus sigma 3 by 2. So that is sigma 1 plus sigma 3 by 2 from the center. So in triangle O dash AB, sin phi is equal to AB divided by, this angle is 90, AB divided by O dash A, and this O dash A can be written as O dash O plus OA, and sin phi is equal to AB. So AB is, this is the also radius of the Mohr circle, sigma 1 minus sigma 3 by 2, and O dash A can be written as, if I take this cos phi is equal to O O dash O, so it can be written as C cos phi, because this is C cohesion. So O dash A is C cos phi plus OA is sigma 1 plus sigma 3 by 2. So cos phi is this one, and cot phi is equal to this by this. So it is not cos phi, cot phi. So if I multiply, sigma 1 minus sigma 3 by 2 is equal to C cot phi into sin phi. So it is cos phi plus sigma 1 plus sigma 3 by 2 into sin phi. So sigma 1 by 2, and this sigma 1, if I take either this side, so sigma 1 by 2 sin phi is equal to C cos phi plus sigma 3 by 2 plus sigma 3 by 2 sin phi. So if sigma 1 by 2 common, then 1 minus sin phi is equal to sigma 3 by 2 if I take common, so sigma 3 by 2 1 plus sin phi plus C cos phi. So sigma 1 into 1 minus sin phi can be written as sigma 1 into 1 minus sin phi is equal to sigma 3 into 1 plus sin phi plus 2C cos phi. So sigma 1 is equal to sigma 3 1 plus sin phi divided by 1 minus sin phi plus 2C cos phi divided by 1 minus sin phi. So sigma 1 is equal to sigma 3 1 plus sin phi into 1 minus sin phi. We know this is the passive earth pressure coefficient, which can also be written as tan square 45 plus phi by 2 plus 2C. If I write like that, 1 plus sin phi into 1 minus sin phi, 1 plus sin phi into 1 minus sin phi. So 1 minus sin square phi, 1 minus sin square phi is cos square phi, so it is cos phi divided by 1 minus sin phi. So sigma 1 can be written as sigma 3 1 plus sin phi divided by 1 minus sin phi plus 2C. 1 minus sin phi cancel, so it is coming square root of 1 plus sin phi divided by 1 minus sin phi. And we know that 1 plus sin phi by 1 minus sin phi is the passive earth pressure coefficient, which can also be written in tan square 45 plus phi by 2. So sigma 1 is equal to sigma 3 tan square 45 plus phi by 2. If you rationalize this, so it will come tan square 45 plus phi by 2 plus 2C tan 45 plus phi by 2. And we have seen 45 plus phi by 2 is the critical angle or failure angle. So sigma 1 is equal to, so this is very important relation between the major principal stress, minor principal stress, cohesion and angle of internal friction. So sigma 1 is equal to sigma 3 tan square alpha plus 2C tan alpha, where alpha is the failure angle, and it can be written as 45 plus phi by 2. So I am going to discuss another very important theory, that is Mohr-Coulomb theory. So Mohr-Coulomb theory, according to this theory, shear strength of soil depends on the cohesion between the particle on critical plane, angle of internal friction between particle, which accounts for interlocking resistance and frictional resistance, and the normal stress on critical plane or failure plane. So according to Mohr-Coulomb theory, shear strength of soil depends on cohesion of soil, angle of internal friction phi, and the normal stress on critical plane or failure plane, which increases with depth of soil. So according to Mohr's, let S be the shear strength of soil, sigma n be the normal stress, C be the cohesion of soil, and phi is the angle of internal friction. So according to Mohr-Coulomb theory, S is equal to C plus sigma n tan phi. So this S is equal to C plus sigma n tan phi. So let us assume this is Y. So Y is equal to mx plus C, where C is the intercept and tan phi is the slope. So if I draw the Mohr-Coulomb envelope, failure envelope, so this is the shear strength and normal stress, and C is the intercept. So this is the Mohr-Coulomb envelope and intercept is C, and the slope of this line Mohr-Coulomb envelope is angle of internal friction. So this is called Mohr failure envelope. But this theory is incomplete, because if there is a water table, then this term like cohesion, normal stress and angle of internal friction will be reported in the effective term. But Mohr-Coulomb has given the expression of directly in terms of total cohesion, total normal stress and total angle of internal friction. So the above theory is incorrect for the condition where the water table is present. Hence the above theory is modified and improved by the father of soil mechanics, that is Terzaghi, which is called modified Mohr-Coulomb theory. So the above expression is incorrect for the condition where the water table is present. Hence the above theory is modified by and improved by father of soil mechanics, Dr. Carl Terzaghi, which is called modified Mohr-Coulomb theory. So what is modified Mohr-Coulomb theory? So according to modified Mohr-Coulomb, shear strength of soil is equal to effective cohesion plus effective normal stress into tan phi dash, where C is the effective cohesion, sigma n dash is equal to effective stress on the critical plane And we know that in the soil mechanics chapter, if total stress and effective stress, so effective stress is equal to total normal stress minus pore water pressure. So with the help of pore water pressure, we can compute the effective normal stress, and phi dash is the effective friction angle, effective angle of internal friction. So if I draw Mohr-Coulomb envelope once again, so the Mohr-Coulomb envelope will be same, but the term will change. So this term intercept is effective cohesion, and the slope of this Mohr-Coulomb envelope is the effective angle of internal friction, and this is modified Mohr-Coulomb envelope. So these are the facts about the Mohr-Coulomb envelope, but there is some limitations of the Mohr-Coulomb also. So what is the various limitations? So limitations of Mohr-Coulomb theory. The first limitation is Mohr-Coulomb theory is approximated to be a straight line which is found invalid for over-consolidated soil. So what is over-consolidated soil? So I told you in the soil mechanics class, over-consolidated soils are those in which the over-consolidation ratio is greater than 1, and over-consolidation ratio is the ratio of past overburden pressure to the present overburden pressure. So the first limitation, Mohr-Coulomb theory is approximated to a straight line which is found invalid for over consolidated soil, and in practical results shows that Mohr failure envelope in over consolidated soil, that is OC soil, is found to be slightly curved. So if I draw for OC soil Mohr-Coulomb envelope, this is the normal stress, so it looks like that for OCS soil, over consolidated soil. Second limitation of the Mohr-Coulomb is that the analysis in 2D only we are considering major principal stress and minor principal stress, but in actual stress condition in soil in 3D, the intermediate stress also acts on the soil. So the second limitation, the analysis is two-dimensional, that is sigma 1 and sigma 3 are considered, whereas actual stress condition in soil are three-dimensional, in which sigma 2 is equal to sigma 3. So dear students, today I have discussed about the various, what is Mohr-Coulomb envelope and what is Mohr-Coulomb equation, and after that I have discussed modified Mohr-Coulomb equation, and before that I have derived the equation of normal stress and shear stress, and we have seen the relation between normal stress and shear stress and angle of obliquity. After that I told you that different Mohr circle, that is Mohr circle for the clay, Mohr circle for the sand, and Mohr circle for the silt. And in the Mohr circle of silt, I have derived the relation between the major principal stress, minor principal stress, cohesion, and angle of internal friction, that is sigma 1 is equal to sigma 3 tan square alpha plus 2c tan alpha. So in the subsequent class I will discuss various drainage conditions, and after that I will start the laboratory test, that is direct shear test, triaxial test, unconfined compressive strain test, and vein shear test. And after that I will start laboratory test, that is vein shear test.